Hello, everyone. Good morning, good afternoon, good evening. Let's do a sound check. Nazan, good morning. How is everything?
Good morning. Everything is fine. Thank you.
Fantastic. It looks like we've got a huge crowd. This webinar is oversubscribed. Folks, we did not realize how popular 4761A, the new version, plus ARP4754A would be in your lives. So clearly, it was a good idea to do this. We have a very busy, aggressive 50-minute presentation. This is condensed from our training that we do, Nazan and I, for Taos and AFuzion. So we hope you enjoy. We have planned for 10 or 12 minutes of questions at the end. As usual, we get many more questions as we can answer. So instead, we simply will try our best to answer those questions and get back to you via email if we can, okay? So we are good to go. With this, let's begin to understand and apply the new mandatory, and we'll explain why it's mandatory, ARP4761A and ARP4754A. First, a quick couple minutes about your presenters here. This is myself, Vance Hilderman. I'm the founder and Chief Technical Officer of AFuzion. I have several college degrees. I founded 3 of the world's largest avionics aviation companies, and I've trained over, today, about 21,000 people in DO and ARP4754 and things. So quite a bit. I've worked on many aviation projects. I think I've worked for almost all the world's largest aviation companies, and many of you have what I call the worst book on aviation certification. At the time, it was the only book. Today, maybe it's the second or third worst book, who knows? But anyway, I've been around the block a bit, and let me introduce Nazan to you. So she also is very well educated with bachelor's, master's, and MBA. She's the founder of Taos Certification and Consulting, and she's worked in both industry and military for over 20 years. And she's provided training also and consulting to many, many companies in the aviation and safety critical worlds to establish their design assurance system. A key point is that Nazan was a key individual contributor to the very standards that we're talking about today, 4754A and 4761, the safety assessment process, aircraft development, avionics processes. So she's incredibly knowledgeable, and I'm really proud to be her partner in business and also in the training and consulting here. With that, let's begin. The purpose of this webinar, like all of our training webinars, is to explain in real terms. Anyone can read the book. Instead, what does it really mean, these books? Why are these ARPs important? And why do we call them mandatory? Try to gain an overview of ARP 4754A and 61. Understand their interactions. It's really part of what we call the aviation development ecosystem. It's the interplay of safety, systems, software, hardware, security, many different considerations. Security is an interesting one. We won't be addressing that today, but DO326, 355, ED202, all of those, these are mandatory for us going forward as well. We have another free technical webinar in 2 weeks that we'll try to record also, but you can sign up for that as well. That'll be aviation security. Our goal here is to make better avionics faster and cheaper while achieving compliance with these standards. Okay, so you know how these work. Look at these questions. We have a quick, easy, truly 6 questions. Ponder these questions. We're going to answer them during this webinar, and we'll provide the answers at the end. See how in tune you are. You're all smart engineers. You were smart enough to wake up early, late, whatever, to tune into this webinar. The first one, true or false? 4754A and 4761 are generally optional for aircraft and systems. Number 2, 4754A applies directly to avionics software and hardware. True or false? Number 3, 4754A process assurance performs systems testing and also manufacturing and maintenance inspections. True, false. DAL, development assurance level, it's called many things. Criticality level, the old design assurance level. The real word is development assurance level, but just call it DAL for short. DAL is assigned to the effort of mitigation of systematic errors which could lead to failures. Number 5, DAL assignments depend on the failure condition classification, the number of independent failure paths, and their associated independence attributes. And the last question, 4761 provides methods for safety assessments to show compliance with certification requirements. 6 easy true-false questions will provide the answers in 45 minutes, but if you pay attention, you'll get the answers during this 1-hour training video. Okay? First of all, I'd like to turn it over to Nazan, who will tell us why these standards are mandatory. Nazan?
Yes, thank you, Vance. We call it mandatory because both ARPs supports aircraft certification process by showing compliance with 1309 requirements. The guidelines in ARP4754A were developed in the context of large airplanes, Part 25 aircrafts, but it can be applicable for other parts like 23, 27, 29, and 33 and 35. That means small aircrafts, rotorcrafts, engine, and propeller. ARP4761 provides safety analysis techniques to identify failure condition, their effects, probabilities, and criticality levels. We called in ARP's development assurance level for each function, hardware, and software. And ARP4754A provides development assurance for functions and systems only, and sets objectives based on those development assurance levels. Next slide, please, Vance. And FAA also issued an AC 20-174. It recognizes ARP4754A as an acceptable method for establishing a development assurance process. And also FAA AC 1309 Arsenal version and EASA EMC 1309 recognize both ARPs as an acceptable method for showing compliance. Next slide. And I am giving the words to Vance for 4754A presentation.
Thank you, Nazan. Let's talk about 4754A just a minute. Nazan summarized 61. Now, 4754, the prior version, was certification considerations for highly integrated or complex aircraft systems. What a word, right? Highly integrated, complex, very subjective. That was the issue. While generally mandatory, it really wasn't enforced. Came out in 1996, right about the time aircraft complexity is really dramatically increasing via hardware, software, and the architecture. We needed a new document, 4754A, one little letter, the A version, the next version. It was almost 14 years later, it came out, 2010, but it was mandatory in 2011. Look at the name, Guidelines for Development of Civil Aircraft and Systems. However, it's now being applied to military, other industries. 4754A was guidelines, and so we need to consider the overall aircraft operating environment and functions by considering continuously the system safety assessment. So it includes the validation of requirements, verification of the design implementation, and also process assurance, which remember is quality assurance on steroids, right? We call it process assurance because it's more than just the developmental QA. It's all aspects of the integration, suppliers, audits, and everything. Now, let's compare 4754 to 54A. On the left, 54. On the right, 54A. Any questions? Just kidding. Take a look. Here, section 3, it's about development planning. We really have to have plans. Remember 178254, it's based on the fundamental 5 plans. Well, systems and aircraft are a little different. We have to show that we have certification considerations fully planned, and then we assess our implementation of those. Look at section 4. It's not just the avionics systems anymore, it's the aircraft, how they integrate, how they interface with each other. Section 5, the integral processes. Remember, integral processes, correctness process. It's verification, validation, configuration management, quality assurance, or as we call it, process assurance. And then the appendices. We have real objectives, okay? We have a safety program plan. We have FDAL and IDAL, big words. Nazan will explain those. And then we have the appendices. So we'll go ahead and talk about that and how we move those. And it's going to be really important to see how the new version, just coming out here, it's all done, should be released this year, 4761A, how that has changed also. But look at the model of 4754A. Recognize this? Look at the lower left. We start with the concept. That flows to the aircraft. So now our aircraft airframers, Boeing, Airbus, Embraer, Cessna, Augusta Westland, all over the world, Mitsubishi, Comac, we have to consider 4754A incorporation from the beginning at the concept and apply it to the aircraft. It's not simply flowed down to the avionics producers. Then we allocate the functions of the aircraft to various systems, thrust, control, landing. Then we develop the corresponding system architectures and aircraft architectures. We allocate system requirements to specific items, implement those items, and then we have the document suite. Look at that, it's rather a progressive waterfall. But look at the top, what comes first? In order to do that, we have to have planning. That's the upper left. But then we have the integral processes. Remember those? It's the safety assessment, determining which DAL, which criticality level applies. And then requirements, validate those requirements. Configuration management, process assurance, and certification. Those are continuous in the background. That's the ecosystem, and it affects the hardware and software, as we'll see in a moment as well. Well, right here, for safety critical development, we've got three key processes. This is identical throughout the software 178C, hardware 254, CNS ATM ground-based systems DO278. We have these three processes. In red and small on the left is planning. Planning comes first. Then is the development process. Development is not just implementation, it's safety, it's requirements. Do we have the right requirements? That's validation. It's implementation. But then look in the background, the continuous safety, configuration management, process assurance, validation, verification, certification. Those are performed in the background continuously. Why is that green? Great question. I made it that way because green is the color of American money. All of our money in America is green. Green means money. The most expensive part of systems development really is the correctness process. The least expensive is the planning. It's the smallest, but it's the most important. If we don't have good plans, we cannot assess to those plans. Okay? So let's look. There are 6 basic steps of 4754A. First, prove that we have applicable adherence to regulations and certification guidelines. So we have to plan our aircraft and our systems development lifecycle with detailed plans. We have to show how we're going to have interfaces within that ecosystem. Then, and next, we start these safety activities. We implement them. We follow 4761, and we'll be explaining those in just a moment. We have to define, then justify the criticality level, the criticality, the design assurance level, the DAL, the development assurance level. Wow, 6 words, they all mean the same thing. DAL, how critical is it? Then define the system architecture and the requirements. Validate those. Remember, verification. Do I have an implementation that meets the requirements? Validation. Do I have the right, correct, complete requirements? They're equally important, but in our opinion, validation is more important. It's fundamental in 4754. If we don't have the right requirements, it doesn't matter if we implemented them, right? Number 5, then perform verification. Does implementation meet those requirements? And ensure we have configuration management so we know who made every aspect of the system and safety processes for everything that's flying. Can we rebuild it 30 years later? And finally, implement process assurance. That's quality assurance on steroids, remember? And prove the transition criteria, entry, exit. before we progress to the next stage within this process, have I met all the entry and exit criteria? That's transition criteria. Engineers follow the transition, QA assesses and records it. So the planning element, let's talk about 2 slides here. There's 8 steps total. Number 1, development planning. What are the process methods for establishing our architecture, either aircraft or system, subsystem, or item? How are we going to develop it, integrate it? How are we going to implement it? How will we show compliance with 4754, 4761, all of the TSOs, technical standard orders, STCs, supplemental type certificates, all those aspects that apply, plus the EASA, FAA, CAAC, Transport Canada, whatever our certification authority is. And remember, folks, military is adopting this as well, so military is involved with that. So we have to define the safety scope that's applicable to the aircraft or system, and we'll use 4761 for that. We'll see in a moment. We have to show that we can manage the requirements, define how we acquire them, how we manage, how we determine the safety requirements, then validate. What are the methods I'm going to use to ensure the requirements and the assumptions are correct, complete, feasible, unambiguous? Then implement. That's often through 178254. You can look at our other training videos. Just go to YouTube if you want to watch those and download those on 178254. But implement, verify. What are the processes and criteria used to assess that the implementation meets the requirements? Number 6, CM. What are the process activities that we'll use to manage the whole development configuration items, safety, systems, software, hardware throughout that life cycle, including changes? How will we ensure that no unwarranted changes are made? How will we ensure that all anomalies were investigated, tracked, and that we know what the status is and their effect on safety? Anything that has a potential safety effect has to be considered within the safety context. Safety engineers, documentation. Number 7, process assurance. Define the independent activities that we use to ensure development activities follow the processes and plans. And then finally, certification. Define how we will perform this certification for our project, be it the aircraft, avionics integrator, the system developer, or the item developer. Those are the 8 basic steps that we have to capture within our plans. We can put those all in one plan. That would be rather foolish, but it's better to put them in separate plans so that we can properly allocate and manage. The good news, folks, once each of you has these good plans in place, you should have portability for future projects. You should be able to use them with very few changes on the subsequent projects. So do it right the first time. You won't have to do it again. The ecosystem looked like this. Before I turn it over to Nazan to take a deep dive into 4761, let's consider, we call this the horse. If you've been to our training before, it's a horse. The upper left is the head of the horse. That's the safety assessment. That follows 4761 and eventually this year, the new 4761A. What are the functions of our system? What's the architecture? How much redundancy? How do I do switchover, voting? How do I detect errors? What are my inputs and outputs? Then finally, what's my FDAL, my functional development assurance level? Naz will explain. Once we define that, we have the system development process, 4754 or ED79 in Europe. That's the body of the horse, the muscle, the organs. We allocate those system requirements, including safety, allocate to software, hardware. Then we implement software 178 or hardware 254, ED80 in Europe. But look at those feedback loops, the red lines. That's part of the ecosystem that 4754 and 4761 mandate, okay? We have to prove that we not just implemented them, but that we actually applied them on a continuous basis. With that, I'd like to now turn it over to Nazan, who will take us through 4761 and A. Nazan?
Okay. ARP4761 describes the guidelines and methods for performing safety assessment and analysis. As we see, we use that guidelines as showing compliance with certification requirements. 61 applicable for all aircraft types, small, large aircrafts, rotorcrafts, UAVs, military aircrafts, and also it can be applied for engine and propeller. So the current version is initially published in 96, but the A version will be published in this year, Q3. Next slide, please, Vance. Here we compare the both current version and draft 4761A. As you see, we will have more appendixes in the version A. So the highlighted red ones are new assessment and analysis, preliminary aircraft safety assessment, and aircraft safety assessment, new assessments, and model-based safety analysis, cascading effect analysis are the new analysis techniques, and DAL assignment details is a safety process. Therefore, detailed information about DAL assignment will be moved from 4754A to 4761 as an appendix in the A version. So the rest of the other appendixes will be kept the same, but updated as needed. Next slide, please. ARP4761 applies to everyone, from aircraft manufacturer like Boeing, Airbus, Bombardier, TAI, or STC holders, system integrators like Honeywell, Rockwell Collins, equipment suppliers, a wide range of avionics equipment providers, certification authorities, FAA, EASA, Transport Canada, and other CAAs. Next slide. In 4761, there are safety assessment and safety analysis. I called safety assessment as system safety trio. Aircraft level trio, aircraft functional hazard assessment, preliminary aircraft safety assessment, aircraft safety assessment, and system level trio, system functional hazard assessment, preliminary system safety assessment, and system safety assessment. Other safety analysis techniques in 61 supports those trios. So let's quick overview of each one. Aircraft functional hazard assessment assesses aircraft functions, identify aircraft functional failures and their effects, then classify the severity of each failure condition. Preliminary aircraft safety assessment, which is new in version A, analyze the proposed aircraft architecture to determine how failures identified in aircraft FHA could occur. Aircraft safety assessment ASA is new in version A also. It is the final assessment, collects, analyzes, and documents verification evidences for aircraft implementation. It shows that the failure conditions identified in aircraft level FHA have been addressed and safety requirements established by PASA, Preliminary Aircraft Safety Assessment, are met. When we look system level trio, system functional hazard assessment examines the system functions to identify potential system functional failures. Preliminary system safety assessment, PSSA, examines the proposed system architecture. It evaluates the failure condition identified by the system functional hazard assessment and safety requirements allocated from PASA, from aircraft level. Through the PSSA process, safety requirements for system, subsystem, hardware, and software items are generated. System safety assessment, as ASA, collects, analyzes, and documents verification evidence for system implementation to show that the safety requirements established by PSSA are met. As you see, those assessments are function-oriented. Therefore, function development and functional architecture is very important to perform effective safety assessments. So, good system engineering, according to 4754A, is vital. Next slide, please. There are a number of analyses in 4761. Fault tree analysis, dependence diagram, and Markov analysis. Fault tree analysis supports PASA and PSSA. It evaluates a proposed aircraft and system architecture to assign hardware failure probability budget. It also identifies functional failure set in order to assign development assurance levels during the PASA and PSSA process. It shows compliance with qualitative and quantitative safety objectives as part of the SSA and ESA. Failure mode and effect analysis is a bottom-up analysis technique. It identifies failure modes and failure effects. It can be developed at any level, like function, system, equipment, or piece part. FMEA may be performed for any reason, but in 4754 appendixes, it addresses to support safety assessment process. Cascading effect analysis is a new analysis in 4754A. It is a qualitative bottom-up analysis techniques. It evaluates an initiating conditions and its total effect on the aircraft. Because of the system dependencies, an initiating condition may propagate from impacted systems to other connected systems, like resource system failure modes, like shared component failure modes. Model-based analysis also is a new technique in version A, and it performs safety analysis using failure propagation models. It is a software application, generates outputs such as failure sequence, minimal cut set, or other results. Common cause analysis establish physical and functional separation, isolation, and independence requirements between systems and items, and it verifies that these requirements have been met. Next slide, please. Now, development assurance. What is development assurance? Development assurance is a process, planned and systematic actions that provides adequate level of confidence that error, I'm just emphasizing error, in requirements, design and implementation have been identified and corrected. Understanding of error contribution to a failure is important. Failures can be divided into two categories, systematic failures and non-systematic failures. Mitigation of non-systematic failures, like random hardware failures, is performed by setting safety qualitative and quantitative requirements. But systematic errors that lead to failure are not associated with any physical changes and will always occur when a given set of conditions are satisfied. Software failures are always systematic. Specification errors, requirement errors, design errors, component deficiencies, all those are systematic errors. So for simple systems, error can be detected by exhaustive testing, but for complex and integrated systems, exhaustive testing may be impossible or be impractical because of the number of tests, and all of the system states cannot be determined for those tests. For this type of complex system, compliance are shown by the using development assurance process identified in 4754A. Next slide, please. There are two types of development assurance level in ARP4754A, FDAL and IDAL. DAL sets level of rigor for development assurance activities, FDAL for function and system, IDAL for hardware and software. Traditionally, development assurance was performed at component, hardware, and software level by DO 178 and 254. But for today's complex systems, it was insufficient. Therefore, additional development assurance process for aircraft and systems is defined in ARP 4754A as FDAL. So 4754A defines the process to apply it only for FDAL, and 4761 safety processes identifies FDAL and IDAL. Next slide, please. ARP 4754A defines two ways to assign DAL. One way is assignment without considering the system architecture, and another way is assignment considering architecture, system architecture. With this option, independence between system and components must be assessed. Next slide. For a good understanding of FDAL and IDAL assignment, we need to understand definition of functional failure set, members, and independence. Functional failure set equivalent to fault-free minimal cut set. Minimal cut set, as we know, the smallest combination of basic events, if they occur, will cause the top event to occur. So the member of FSS can be an aircraft system function or item that may contain error causing its loss or malfunction. So independence is a concept, minimizes the likelihood of the common modes error between aircraft system functions or items. So FSS, it looks for error point of view compared to fault-free minimal cut set. Next slide, please. In 4754A, there are two tables. First one explains how we assign DAL without architectural consideration. According to this table, FDAL is assigned to top-level function based on its most severe top-level failure condition classification, identified in FHA. So, classification using this table may result in more conservative assessment. If the failure condition classification in aircraft or system FHA, if it's catastrophic, we assign DAL A. For hazardous, B. Major, C. Minor, DAL D. No safety effects takes the DAL E. Next slide. Second DAL assignment table in 4754A, consider the architecture. Once an aircraft FDAL is assigned to a top-level function based on the first table, the architecture of system functions is examined to determine the development assurance level of those system functions. If a catastrophic failure condition could result from a combination of possible development error between two or more independently developed aircraft system functions or items, so we can use option 1 or option 2. So one members can get FDAL A and the other one can get FDAL C, or both the members can get FDAL B. Let's just imagine we have a navigation and communication system. Both systems provides flight data. So since those two systems independent from each other, we can use either option 1 or option 2. So we can assign the navigation system FDAL A, communication system FDAL C, or both systems can get FDAL B. Or for primary flight display, for example, in our design, we have primary flight display and standby display. Since both displays are independent from each other, we can use this table, option 1 and option 2. Primary flight display can get FDAL A, and standby system can be assigned FDAL C, or both systems can get FDAL B. We can use option 1 and option 2 as long as showing the members are independent. Members mean systems like navigation and communication, primary display or standby display. Next slide. So it is the summary slide of aircraft level top-down assessment. So we start with aircraft function list, and regulatory objectives and requirements goes into aircraft FHA. We evaluate aircraft functions as an output of aircraft FHA, aircraft failure condition effects, classification, and aircraft function criticality, FDAS, without considering architecture. So we use table 1. And then those requirements goes into PASA, preliminary aircraft system safety assessment. So we evaluate proposed aircraft architecture. As an output of PASA, aircraft function FDAS, system function FDAS, safety requirements, probability budget, independence requirements generated. Next slide. And in this slide, we summarize the system level top-down assessment. So aircraft OEM perform their FHAs and PASA. So all the requirements and system list goes into the system provider, system FHAs. So system FHAs evaluate system functions. System failure conditions, effects, and classifications is generated as an output of system FHAs. Those failure conditions and classifications goes into PSSA. PSSA evaluates proposed system architecture. So as an output of PSSA, system function FDALs, IDALs, in this case, we assign DALs for hardware and software by preliminary system safety assessment. Safety requirements, probability budget for components, equipment, items, and independence requirements generated by preliminary system safety assessment. Next slide will be an example. Here is very simple example for DAL assignment. From an aircraft function list, we take control aircraft energy function. So, and decompose this function into subfunction. And we will take provide deceleration on ground function as an example. In next slide, we will perform aircraft FHA, considering this provide deceleration on ground function. Next, please. Provide deceleration function is one of the aircraft level function. We assess all the failure conditions. Total loss of deceleration capability and inadvertent deceleration leads to catastrophic. So we use table 1. Since its classification is catastrophic, we assign those functions, those failure condition FDAL. Next slide. And these functions and classifications goes into PASA, Preliminary Aircraft Safety Assessment. In this assessment, we evaluate aircraft, proposed aircraft architecture. In our example, provide deceleration on ground function performed by engine, thrust reverse system, ground spoiler system, and wheel brake system. Now, in the next slide, we will evaluate those system interaction in fault tree. Next, please. In fault tree, we evaluate and we generate a minimal cut set, functional failure set. As we see on minimal cut set, there are redundant systems. Those are redundant systems. It's independent systems. So the failure of thrust reverse and speed brake, or failure of thrust reverse and wheel brakes, leads to total loss of deceleration capability. Since we have 2 members in FSS, we can use table 2, option 1 and option 2. We can assign one system level A, the other one level C, or both systems can get level B. But before we finally assign DAL, we have to assess all failure conditions. And next slide, we will see how it changed the allocation of DAL. Next, please. And here, another failure condition, remember, it was catastrophic, inadvertent deceleration after V1 decision speed. So in fault trees, minimal cut set, we are seeing all of the systems is leading to inadvertent deceleration. So single member FSS. In this case, we cannot get credit from architecture. We cannot use option 1 or 2. We have to assign each system level A. Thrust reverse FDAL, spoiler FDAL, and wheel brake FDAL. So we know deceleration function is FDAL, wheel brake systems is FDAL. And the next slide, we will go more deeper in the PSSA process. So now we know wheel brake system is FDAL, and we assess proposed system architecture. System has complex BSCU control computer, braking system control unit computer, which leads to inadvertent braking, which is catastrophic. BSCU has 2 command and 2 monitor channels, independent from each other. This is the proposed architecture, right? In this case, we can use table 2, option 1 or option 2. In our example, we take option 2 and assign command and monitor software and hardware IDAL B. So it's up to designer how the proposed architecture goes into preliminary system safety assessment. DAL assignment, it depends on the architecture and how we just shape the design. So in the next slide, we will summarize DAL assignment result. So here we know from aircraft FHAs, deceleration function is catastrophic and we assign FDAL. And then we know braking system leads to catastrophic because of the inadvertent braking. We assign FDAL. We know braking system control units is a complex systems leading to inadvertent deceleration itself. So we assign FDAL-A. So FDAL-A should be managed by 4754A. We use 4754A development processes to mitigate the errors in those systems. And for IDAL, command and monitor hardware and command and monitor software gets the IDAL-B, and we should use for development assurance process DO178 and DO254. And next slide is presented by Vance.
Thank you, Nazan. That was a great synopsis. So folks, you've had a good dive into 4761. By the way, if you'd like more information, we have a very good white paper from Nazan and I that we can distribute to you, and also our training sessions. You can look those up. So let's look here at the development assurance process objectives from 4754A, a synopsis. This is contained in Appendix A. The key here is if people can die. Remember, this is aviation. We don't like to talk about dead people, but that's what happens when mistakes are made. So if people can die, it's a level B minimum development assurance level. If the airplane has a probability of crashing, then it's level A. Okay, so those are serious, level A and level B. And the key here is that for level A and B, again, if there's a potential for crew to die, level A, passengers, level B, we need all of these outputs. The development plan, certification plan, safety program plan, validating those requirements and verifying those requirements, configuration management of all the above, and process assurance. Now, the key here, it says recommended. That's interesting. That's like your parents recommending that you get sleep at night. If you don't, there's a big problem, because really a good way to look at the R in recommended is as required. It doesn't say required, because required is a subjective term potentially with the respective certification authority. So instead we use the word recommended. But trust us, in our experience, we think that the cert authorities require this 99% of the time. So a good and safe interpretation is when you see the word recommended, it's really required. Now, even for FDAL-C, these should be recommended, should be done, because remember, today's level C system could be tomorrow's level B system. If you're making the systems or the items, you really don't have much control over how they're integrated and used within the aircraft. If we want to reduce pilot workload, increase automation, that level C system could become level B, or the level B could become level A. That's part of the safety assessment process of 4761. So now, let's consider the safety assessment process objectives. Again, if people can die, they're recommended. But see that asterisk, that little orange asterisk in the upper right behind recommended? That means we need independence there in addition. So independence is done when a different person, doesn't have to be a different company, different site, even a different group, but a different person using an independent process, okay? So a different person other than the creator or developer of that item. So what we need is the aircraft FHA, functional hazard assessment, at the aircraft level. That's going to come and be controlled by the airframer, Boeing, Airbus, Embraer, Augusta-Westland. Then we need that system FHA. Now, that's going to be a collaborative effort with the integrator, possibly airframer, but absolutely the avionics developers as well. Same with the PASA, preliminary aircraft safety assessment. That's the airframer, but look at the PSSA, preliminary system safety assessment. That is where the avionics developers come in and find the mid-level architecture, backup, health monitoring, safety requirements. They feed those back into the PASA and the integrator, and that's a real key with 61A. Think of A meaning aircraft. It's a aircraft level integration of the ecosystem. So it's that cooperation between the aircraft people, the integrators, and the system item developers. Then the system safety assessment, aircraft safety assessment, then the particular risk assessment, common mode analysis, zonal safety analysis. So particular risks, lightning, bird strikes, common mode. Do I have one failure that causes a violation of my redundancy. For example, putting a primary and a backup controller in the same conduit, the same tube. A single point failure would cause loss of both primary and backup. So that would be a common mode analysis that we have to look at. Then zonal safety. Think of space. If I have my coffee pot right above my flight bay, avionics bay, and my coffee machine leaks water, well, the avionics didn't cause the crash, but the water did, the coffee pot, you see. So consider the zonal safety aspects, installation, maintenance, all of those things as well. Now, validation of requirements. This is key. Remember, are the requirements correct, complete, feasible, unambiguous? So I need to prove that I have criteria. I need checklists. I need processes. I need to have, again, recommended and with independence of validation results. Have I validated the aircraft item requirements? Are they complete and correct? Do I have validation results? Are my assumptions justified and validated? Then, what about derived requirements? Now remember, derived is a funny word, even for native English speakers like Americans. Typically, derived means to come from, and it does, but typically, derived requirements don't necessarily come from a parent requirement. They do not. They come from a consideration by a developer or a safety engineer to add an architectural consideration, system consideration, software hardware consideration that may not be directly related to functionality. Therefore, it's not necessarily decomposed or derived in the official sense from a parent requirement. It's derived from that safety engineer or that hardware software system engineer's desire to force a certain implementation. That's a derived requirement. Derived requirements, they can't be reviewed in the same way as functional requirements in the context of a parent. It's really important to consider, are there any safety effects? So derived requirements have to be proven to have been considered by the safety individual. Proof. Guilty until proven innocent. If you can't prove you did it, you didn't do it. Then validation results. Are those requirements traceable to all those things? Finally, the validation summary and validation metrics, just showing that you have the paperwork in place, that you've really done the compliance substantiation. And again, the results need to be independently a different person than the person creating that work. Now, verification. Again, verification. Does implementation meet requirements? Remember, validation and do I have the right, correct, complete requirements? But verification, have I met the requirements? I need verification procedures, tests, demonstration procedures. I have to show that they're correct. Again, a criteria, a standard that I'm assessing against, and a checklist. Aviation, everything has a checklist. Pilots all know that they can't take off without a checklist. Flight crew needs checklists. We as engineers need them as well. Then I need verification procedures, the results. Prove that the confidence of that function is there, and I have no unintended functionality and no impacts to safety. Then, procedures and results. Simply show that my implementation complies with aircraft and system requirements. Then procedures, I've considered the safety requirements, and again, independence with that for level A and level B. Then a verification summary matrix, just like validation, showing where I've substantiated my verification. And then finally, problem report summary. Do I have any open issues? Did I have any changes? Were there any anomalies, potential or real? What was their impact on safety? Remember, it's very easy for us, the original developers, to do this. It's very difficult for the next team who comes 1 year, 29 years later and makes changes and needs to investigate. So we need to leave good breadcrumbs, a good trail. That trail is the checklist, procedures, plan, proof that we did it. So think of the people who follow you after you retire. So we're almost done. Just a couple more minutes, then we'll take questions. Common safety process mistakes. Here they are. Number one, the company doesn't provide adequate support for safety assessment or development assurance activities. Okay, in the old days, this was less formal, frankly. Here, we have to show that we have a process, a plan for achieving compliance or equivalence to 4761A and 4754A. The safety process, number 2, need to be incorporated for the system development process. So we can't add safety in later. Think of building a house, a building. We can't improve the foundation, not realistically, after the foundation is built. So I need to know what kind of foundation I have. Do I have earthquakes, tornadoes? How many floors will the building have? I cannot add safety in later. It has to be done before and during the development. Avionics is more complex than building houses and buildings, so we absolutely need that for safety in avionics. Late identification, number 3, of failure conditions. Again, we need to identify them early and build in architecture, health detection, over monitoring, voting, TMR, triple modular redundancy, whatever we're doing early. Finally, inappropriate analysis methods related to that. How can I show that I've really considered not just the obvious errors, but potential single point failures or likely potential combinations of failures? Next one, number 5, insufficient control of vendor safety process. I cannot simply point the finger at my vendors and say they're handling safety. Again, 61A is about the aircraft, the ecosystem, everybody working together and showing that they have. So when I have vendors, and many of us do, they have to have equivalent processes, or they use our processes, meaning yours, ours, and achieve compliance. So there's no weak links. We're building a chain here. The chain is only as strong as the weakest link. So 61 and 54 have to show that all those vendors as well are considered and they don't provide the weak link. And then finally, the last item, number 6, insufficient or lacking independent validation and verification of the safety assessments. So many times safety assessments are done by senior, very knowledgeable engineers, safety engineers. And frankly, we see now as an eye that they're not being properly checked. So that safety assessment is fundamental. There has to be proof of a thorough review, someone who understands the safety process, 61 and 54, and actually validates and then verifies that safety assessment. So folks, congratulations. Those are the key mistakes. There's a few more, but we've run out of time. We wanted to present the main top 6 for you here. That was it. Well, folks, you made it. Here we are, slide 43, answers to the quiz. How'd you do? Number 1, 4754A and 4761 are generally optional for aircraft and systems. True in the past, that is false today. Number 2, 54A applies directly to avionics software and hardware. Not really, okay? Software is 178, hardware is 254. 54A comes first and then after. It's an ecosystem, continuous feedback. So yes, it indirectly applies because we allocate DAL architecture, but no, 54A is at the aircraft and system level. Number 3, 54A process assurance. Remember, that's quality assurance on steroids, vitamins. 54A process assurance performs system testing and also manufacturing and maintenance inspections. Folks, that might be true at Microsoft, Intel, Apple Computer, but it's not true in aviation. In aviation, quality assurance, process assurance is about ensuring that the plans, the standards, the checklists are all in place and meet compliance to the applicable regulations and guidelines. Number 2, process assurance QA is about auditing, assessing. Are the engineers following those plans? Can we prove it? Number 3, have we kept records? Okay, checklists, audit results. And then for process assurance, it's 2 more things that quality assurance doesn't do. It's the manufacturability. Can I reproduce that same equipment or equivalent in the future? And then supplier audits as well. That's process assurance, those 5 things. Number 5, DAL assignments depend on failure condition classification, number of independent failure paths, and their associated independence attributes. That is true. Number 6, 4761 provides methods for safety assessments to show compliance with certification requirements. Absolutely, that is true as well. Okay, folks, I see you've got a good number of questions coming in. Nazan, I don't think we're going to have time for all these. There's lots of good ones. Let's go ahead and start here, shall we? Number 1, my colleagues could not log in. What happened? Okay, several of you put that down. We were oversubscribed, folks. We hope you got that email message. I sent a couple of them out yesterday saying this was far more popular than we ever anticipated, and we're going to send everyone a recording link. Hopefully the recording works well. We also, if Nazan has time, might repeat this in the near future to allow all those folks to participate live who weren't able. And again, we're sorry for that. Let's see. Next question. Nazan, why don't you take this one? This question. Do we need to submit all safety assessment documents to the cert authority for showing compliance?
Right, okay. Well, yes, all safety documents should be available for authority review. And authorities want to track your progress and concur on your decision, like failure condition classification, DAL assignment, assumption that you made, segregation, isolation requirements. You take decision during the development of the process. This is for tracking purpose, but for compliance finding, aircraft safety assessment for aircraft level, ASA, and the system safety assessment for system level with supporting data are sufficient for compliance showing or submit as a compliance document for certification.
Ah, very good. Thank you, Nazan. The next question now, I'll go ahead and take this one. What are common ARP4754A gaps, and what recommendations do you have for closing them? Well, it's a big question. I would say the top gaps, when we do gap analysis, and we've done, oh gosh, over 110 for different companies, the number one gap is in process assurance, not having a strong enough PA or QA team that really knows the guidelines, standards, and ensures the plans are complete and correct with entry-exit criteria. The next one is planning detail. The plans are too vague. We call driving a bus. It's not deterministic, too subjective. The third gap is probably safety requirements. Not enough detail, not enough consideration. They're added after the fact, or there's no proof that they were. Other gap is common is checklists. We need checklists, and we need to have detailed checklists to prove that we met the compliance. So we need detailed checklists for all the activities the engineers do. Remember, safety, systems, all the software activities, hardware activities, implementation, CMQA, everything needs a checklist. Last one, probably, performance testing at the system level. Okay, we really need to have better performance requirements, single event upsets, error processing, max bandwidth, timing, resource use. Those requirements are quite often weak, and therefore the tests are weak or subjective. Some companies do it well by tribal knowledge, most don't. Okay, and just validating those requirements. Okay, so those are the common gaps. Next question. Oh, Nazan, why don't you take this? This will be our last question, folks. We're right at 1 minute left. Question, are DAL levels related to probability of failures?
It is a common confusion, always asked. There is no correlation between DAL assignment and probability or failure rates. We assign DAL according to failure classification, not probability. Don't get confused with 1309 probability objectives like 10 to minus 9 should get level A, 10 to minus 7 should get level B. There is no correlation between probability and DAL level. A system may be assigned DAL A, but probability budget may be 10 to minus 6. So the answer is no correlation between those. But the last words I want to say, we need to meet both DAL objectives in DAL level and the probability objectives assigned according to 1309 requirements. So both should be met during the certification process.
There was one important question. It looks like about 5 people asked some form of it. So I'll take the last one. Can you please clarify the difference again between verification and validation? Thank you. This is so common, so easy, and so incorrectly applied so often. The joke is, what did you do today? Oh, V and V. Well, which did you do? V or V? Yes, I did V and V. No, verification or validation. Oh, I don't know the difference, so I just call it V and V. Isn't that what everybody says? It's really simple, folks. Verification. Does implementation meet requirements? Validation. Do I have the correct, complete, feasible requirements? Are the requirements correct? Validation. Which is most important? FAA, EASA. They're equally important, and truly they are. They're both critical links on the chain. Our opinion, validation is more important. If we don't have great requirements, it doesn't matter that we verified them. So validation, do I have great requirements? What is great? Meets the compliance, correct, complete, unambiguous, and feasible, okay? So folks, you did it. 1 hour of 4754A 61. There's a lot more detail we could have gone into. We do this at our public and private trainings. You can look us up. We'll be in many different countries next few months as usual. And come to one of our public training sessions or tune in 2 weeks from now for our aviation security training. Okay, 1 hour webinar. Thank you again, Nazan. It's really a pleasure working with you. I look forward to our next client engagement together. And take care, everyone.
Have fun,
Thanks.
everyone. Thank you.
Good night, good morning, good afternoon, everyone. Bye-bye.
Bye.